All right, so we can start. It's my pleasure to introduce our first speaker of today, Lisa Jeffrey from the University of Toronto, and she'll be talking about Poisson maps between character varieties.
I thank the organizers for inviting me to speak. So this work is joint with Indranil Biswas and Jacques Hurtubise and Sean Lawton, and it's posted on the archive. And please ask me questions. I can't see if you post questions in the chat. Please, somebody tell me if there is a question. So this is outline of what we will do at the end. We get to capping and gluing. General results on character varieties, Poisson structures. So let's suppose that sigma 1 and sigma 2 are two surfaces, possibly surfaces with boundary, and G is a reductive Lie group or could be a compact Lie group. So we're thinking of things like UN, SUN. I will define X of sigma as what we met yesterday, the representation space. So representations of the fundamental group of sigma 1 into the group G up to conjugation. And these spaces are Poisson manifolds. In the case where the boundary is empty, then they are actually symplectic. This was known to Goldman, and so the Poisson, and Atiyah bought Atiyah-Bott's paper on the Yang-Mills equations on Riemann surfaces is where they constructed the symplectic structure in the case where the boundaries are empty. So let's first assume that sigma 1 is included in sigma 2 and F is the inclusion map. Then that induces a morphism from the representation space X of sigma 2 to X of sigma 1, and that will be denoted phi. So we will be discussing properties of this map phi and how it induces, how it is a Poisson map and various special cases. So strictly speaking, F goes between Hom pi 2 into G into representations of pi 1 into G, but because this map is equivariant with respect to conjugation, it induces a map of the representation spaces. So we will sometimes denote a surface with genus G and n boundary components as sigma NG. That's what that means. And we'll write XNG as the representation space for sigma NG. We will show that the map phi is a Poisson map. Okay. So let me begin by describing some basically topological properties. So suppose the surfaces have the same Euler characteristic, and either both surfaces have at least one boundary component or both have no boundary components at all. in those cases, the two character varieties are isomorphic. So the two spaces X and G. So this breaks down into three cases. First, the case where there's at least one boundary component. Second case is where there are no boundary components. All the surfaces are both surfaces are closed. And then there's the case where at least one surface has empty boundary, but not both. So in case one, both fundamental groups are free of the same rank. So the character varieties are isomorphic. The surfaces don't need to be homeomorphic, but they must be homotopy equivalent. In the second case, the Euler characteristics are equal, so the surfaces are homeomorphic, so the fundamental groups are isomorphic, and so the character varieties are also isomorphic. In the third case, let's suppose that the second surface has no boundary and the first one does have a boundary. Oops. In other words, n2 is 0, but n1 is bigger than 0. So the equality of Euler characteristics tells you this, which says n1 is equal to twice the difference of the genera. So that tells you that, let me denote by K the maximal compact subgroup of G. So then the character variety with group G is isomorphic to the character variety with group K. But that's true for G1, but for G2, it is not true that those are equal. So the surfaces are not homeomorphic. So that tells us that the character varieties are also not homeomorphic. In the third case, the Euler characteristics are equal, but the character varieties are not isomorphic. Because for a surface with boundary, the G character variety of a surface with boundary is homotopy equivalent to the K character variety. If the surface has no boundary, then the G character variety is not homotopy equivalent to its K character variety. Okay, the second topological thing that I wanted to describe is that if the two character varieties are isomorphic, then the corresponding surfaces have to have the same Euler characteristic, and either both surfaces are closed, in other words, no boundary, or neither is closed. So that's because if the two character varieties are isomorphic, their dimensions are equal. So suppose sigma 1 has no boundary, has a boundary and the other one does not. Then the G character variety for the first surface, strong deformation retracts onto the K character variety for that surface. But in the case where there's no boundary, X0 G2 of G is not homotopy equivalent to the same thing for K, at least provided that the genus is bigger than or equal to 2. So either both surfaces are closed with no boundary or neither is. this implies that the surfaces have the same Euler characteristic, because the dimension of the character variety is the product of the Euler characteristic and the dimension of the group, plus a term that depends only on the group, but not on the surface. So I will pass to introducing the Poisson structures. Notice that if two character varieties are isomorphic, it doesn't always follow that the fundamental groups are isomorphic. So for example, suppose that you had one group Z2 and the other group Z3. These have the same character variety for representations into SL2C. In both cases, the character varieties are sets with 2 points. So the identity element of the fundamental group is always sent to the identity element of the group. For the group Z2, the non-identity element is sent to minus the identity matrix. For Z3, both non-identity elements are sent to minus the identity element in SL2C. So the representation spaces are the same, although the groups are not the same. That's just an elementary example. So I will pass to Poisson structures. So in local complex coordinates, let's call them z sub I, the Poisson bivector on the character variety can be written this way. The aij's are just functions of the complex coordinates. So let's suppose that alpha and beta are base loops in the surface sigma 1. So they give rise to elements I'll write as bracket alpha, bracket beta in the fundamental group. Let's assume that these base loops intersect in transverse double points. So I've drawn here what happens for the torus with no boundary components. So there are two loops, alpha and beta. And they intersect only once. I'll use epsilon pi alpha beta to mean the intersection number at the point P of these two loops alpha and beta. And I'll write alpha sub P as the curve alpha based at P. I'll denote by R a representation from the fundamental group pi into G. So if F is a map from the group G to the complex numbers, I'll write F sub alpha as just, or F sub alpha of R as F composed with R of alpha. So we'll be discussing Poisson brackets of these F sub alphas. Let's suppose that A is an element of the group G. I'll write F of A. This is an element of the Lie algebra of G. And it basically is the derivative of, we're describing X as an element of the Lie algebra and take the exponential map to send X from the Lie algebra into G. So F of A is an element of the Lie algebra. For UN SUN and actually many other groups, f of A is just the difference of A minus A inverse. It can be an exercise to see that this is actually an element of the Lie algebra. This was found by Goldman. So again, denote the fundamental group by pi. And R is still a representation. So the Poisson bracket of F alpha of R and G beta of R is given by a sum of these terms weighted with the intersection numbers. This result is due to Goldman. Talk about references at the end. So that is the Poisson bracket, and the Poisson bivector will be denoted A and G. So here we're summing over the points where alpha and beta intersect. Notice that if alpha represents one of the boundary, suppose sigma has a boundary and alpha represents one of the curves in the boundary, then it can be chosen so it doesn't intersect any of the generators of the fundamental group of the surface. So that means that F sub alpha, in that case, Poisson commutes with all the other G sub beta. Okay, so if Q is a continuous map, then there's a homomorphism of fundamental groups and a continuous map from the space of representations into G, and this descends to character varieties. This is basically the same thing as the map phi that we had defined earlier. So Goldman showed that if Q is a continuous map between surfaces, and if Q preserves transversality of base loops and preserves double points, then the induced map of coordinate rings is a morphism of Poisson algebras, provided that Q preserves orientation, and it's an anti-Poisson morphism if Q reverses orientations. So this Poisson bracket is given in the case where Goldman basically did the case where the surface didn't have any boundary. Lawton did the case where there was a boundary. This was Goldman's work. And Sikora did also the case where, Goldman did the case where the genus is greater than or equal to 2. Sikora did the case where the genus is 1. And in that case, the Poisson bivector was computed by Goldman and by Lawton for different groups, for SL2C and SL3C. Goldman also found the Poisson bivector for the case of 4 punctured spheres. So genus 0, that's a sphere, and 4 boundary components. And also the case where there is one boundary, genus 1, so a torus with 2 boundary components. So now let us assume that we have an open smooth manifold, not instead of a manifold with boundary. And G is compact, or it's reductive complexification of a compactly group. We fix a base point. The representation R is called reductive if the Zariski closure of its image in the group is a reductive subgroup. This condition is always satisfied if the group is compact. So then XNG is the closure of the XNG is the quotient of the space of reductive homomorphisms by the conjugation action of G. And this is the same thing as the geometric invariant theory quotient. So we'll define a G connection as a principal G bundle over the surface, which is equipped with a connection. Let's let E be a vector bundle over the surface, sigma 1 or sigma 2, which is associated to the principal bundle E sub G through the adjoint representation. Poincare duality tells you that the tangent space to the character variety is the compactly supported first cohomology H1 with coefficients in E. That is familiar from, for example, the work of Atiyah and Bott. There's a natural homomorphism from the cotangent bundle to the tangent bundle, equivalently a 2 form on the representation space. This is obtained by taking the inner product of a 1 form on probably matrix valued or bundle valued 1 form on the surface with a compactly supported 1 form on the surface. So that gives you a compactly supported 2 form on the surface, and then you can integrate over the surface. And we'll denote that by theta. In the case of a compact oriented surface, theta coincides with the symplectic structure on the character variety, which was constructed by Atiyah and Bott. This is in 1983 and 1984. Okay, are there any questions to this point? Hello?
Yes, I don't think that there are any questions so far,
Okay.
at least not in the chat. I guess otherwise just
Okay.
turn on your microphone and ask.
Okay. Then we have maps from, we have maps beta from bundle valued cohomology for sigma 2 to the same thing for sigma 1, and similarly for compactly supported. And the map beta is the same as the map d phi. Phi was the homomorphism that we described earlier. This map results from pulling back 1 forms under the inclusion map from sigma 1 to sigma 2. Similarly, the map gamma with compact support coincides with the dual map, the dual 2 d phi. And this results from pushing forward from sigma 1 to sigma 2 under the inclusion map. And we prove that phi is a Poisson map. So really we use, this is definition, basic result that a map between a map between Poisson manifolds is Poisson if and only if this condition is satisfied. Here, theta A and theta B are the Poisson structures. So basically, you're insisting that DF intertwines theta A and theta B. That's.
Can I just
go ahead.
ask?
Yes, go ahead.
Just what was the condition on the map from sigma 1 to sigma 2? Because here you say it's an inclusion map.
Well, okay, so we had started with the condition where sigma 1 was included in sigma 2.
Okay.
We did describe a more general situation where you had a map called Q, which was a continuous map between two surfaces, and some of our results generalized to that. But in the first instance, assume that the map is the inclusion map. Yeah, here we also talk about a covering map.
So sigma 1 was an open submanifold of sigma 2?
Yeah, we started with the situation where sigma 1 was a submanifold of sigma 2.
And there was a condition on sigma 2 as well, that is an open manifold?
Well, at this point, we had replaced manifolds with boundary by open manifolds.
Okay.
Most things will work in any case for manifolds with boundary, and you should be thinking of just extending. You certainly can think of, if you have a manifold with boundary, just imagine it to be an open manifold. Imagine that you have removed the boundary.
Okay.
Most of the time, that is really the context that we're working with. So let's suppose that phi is a covering map. Define psi by pushing forward the fundamental group under phi from one surface to the other. So then we also prove that psi is a Poisson map. And this proof uses that deep psi sends the cohomology class to its pullback under the map phi. The map dual to d phi sends a compactly supported one form to the sum of its pullbacks over inverse image points under the map's phi. And this form is also compactly supported. So let me describe what I mean by capping. Probably let me fast forward to the pictures, which I can't have at the same time as the text. So the several situations. Here I'm thinking of a surface with two boundary components, and then I glue in a disk over each of the boundary components to close them off. And what that does to the representation space. So capping with disks means in that situation, the map phi is an injection. The image is the union of a family of symplectic leaves. If you cap off all the boundary components. So that's, as I said, you take all the boundary components and you glue a disk over each boundary component to form a closed surface. Second situation, capping with a cylinder. So that means gluing two boundary components of the cylinder to two components of the boundary of the surface. So this produces a surface with two less boundary components, and the genus increases by one. In this situation, the two character varieties have the same dimension. So what this looks like is we have our two boundary components and we've glued a cylinder, we've glued the boundary of the cylinder to each of those. That is, so first we had genus 1, now we have genus 2, but no boundary components. They've been capped off. Third case, capping with a multiple hold sphere. So the resulting surface has less boundary components and the genus also increases. In that case, the map phi is not surjective. In the case where k is bigger than equal to 3. Could be surjective in case B. So here we have genus 1 and 3 boundary components. We've glued a 3-hold sphere to the 3 boundary components, and so we now have something with no boundary components and higher genus. Yeah, I should have drawn this better. So another case is where you have one boundary component with a genus 1 curve. So as long as the group is semi-simple, then the map phi is surjective. Let's see what that looks like. So we have one boundary component, we're gluing it to a 1-hold torus. So here we had genus 2 with one boundary component, now we have genus 0, and now we have genus 3 and no boundary components. Final example is where you're capping with a torus with n boundary components. It's an n-punctured torus. In this case, the map is surjective and is Poisson. So here we have genus 2 and 2 boundary components after gluing a torus with 2 boundary components to the 2 boundary components. We now have no boundary components and genus 4. So finally, I'd like to talk about how you interpret gluing by means of symplectic quotients. So there are one set of spaces whose quotients are character varieties are the Q Hamiltonian spaces of Alexeyev, Malkin, and Meinrenken. So these spaces, for example, DG, the double just means G cross G. G is still a reductive group. And this has an action of G cross G. I'll also write boldface DG, the same space, but now it has an action of just G, not G cross G. This is referred to as the internal fusion of the double. So the action of G cross G on the double is as follows, just left multiplication, right multiplication, so on. And what that does to the 2 form on the double is like so. Here we're thinking of A as a map. You're thinking of A as a coordinate. Theta is the Moiré-Cartan form. So theta you can think of as could think of as A. It could be inverse BA. If you want to think of, this would be matrix valued one form. Star R would mean BA. So this is how the internal fusion X is acted on by G. It's just acted on by the adjoint action. The two form, the action on the two form is like this. Here we're using coordinates A and B. A and B as coordinates in this is still equal to G cross G. Okay, so the Q Hamiltonian space are copies of the double and G copies of the internal fusion of the double. This is just 2G copies, G plus R copies of G cross G. And you have to keep track of what is the Q Hamiltonian action of R plus 1 copies of G on that. So it's basically the A's and B's get acted on by the adjoint action, and U and V get acted on by left and right multiplication. So this Q Hamiltonian space is equipped with a two form and with moment maps, Q Hamiltonian moment maps, which are as follows. Just projection on some of the coordinates with their inverses, and in some cases you need adjoint action. So these moment maps play the role of that if you restrict to level sets of these moment maps and then quotient by the group actions, you recover the character varieties. And you may recover the Poisson structure or symplectic form on the character varieties from the quotient construction. That was the work of Alexeyev, Malkin, and Meinreke in the paper that I cited. So to form a Poisson manifold by gluing two boundary components of a connected surface, we set the values of the moment maps corresponding to the two components to be equal, and then we take the quotient by the diagonal action of the group. So if we started off with a genus 2 surface with two boundary components, we just glue those together. So we now have a genus 3 surface. To form a Poisson manifold by gluing boundary components of two different surfaces, so not the same connected components, we set the values of the moment maps on the two Q Hamiltonian spaces to be equal, and we take the quotient by the diagonal action of the group. So here we have two, well, I drew a one-hole torus and a genus 2 surface with one boundary component. So you, under the quotient construction, you would get, again, a genus 3 surface. just by gluing those two boundary components together. And this procedure can be iterated. So if in the end all the boundary components are glued together, you recover the corresponding character variety is a symplectic manifold. I won't say much about the extended moduli space. That was another way to, it does a similar job to the Q-Hamiltonian spaces of Alexeyev, Malkin, and Meinrinken. I will pass to the references that I discussed. Alexeyev, Malkin, Meinrinken, papers of Goldman, my extended moduli spaces paper, papers of Sean Lawton on character varieties, and the paper of Sikora. So I'll stop there and ask if there are any questions.
Yeah, thank you very much for the talk.
Should I unshare my screen so that I can answer questions?
Maybe it is, I think everyone can see you, and maybe it's good to have the screen here.
Oh, right, okay.
If you want to point at something.
Okay,
so,
okay.
Does anyone have any questions?
So when you glue up, so if you start with these pieces with boundary and you glue them up into a closed surface, then you actually recover the Goldman symplectic structure.
Yeah. Yeah.
That's interesting.
Yeah, you would recover the Goldman symplectic structure on the character variety.
So I mean, do you learn anything about that symplectic structure by breaking the surface down into, I don't know, like the simplest pieces you can?
Well,
pants or something.
Yes, because it's hard to, well, to begin with, the simplest, the symplectic structure is symplectic structure on easiest to describe on torus, because the torus is the only on the torus do you have global coordinates where you can describe the character variety. So probably the easiest, the thing that is most illuminated by this is the fact that really if two of these loops do not intersect, and the symplectic structure is concentrated at the intersection points of the two loops. So if you have functions which come from one particular loop, then they Poisson commute with any, so Goldman, if alpha and beta are disjoint, if they don't intersect, then the corresponding functions Poisson commute. And that is perhaps easiest to see if you break down into surfaces that glue together.
I see. Okay.
Are there any other questions? Maybe I can also quickly ask something. So, I mean, maybe that, I'm not sure if that question makes sense, but does this Poisson structure on the character variety lift to any kind of structure on the homomorphism spaces?
Well, it kind of a lot of these structures come from the homomorphism spaces. And
but they're not smooth, is that right?
You mean the representation spaces are not smooth?
Yeah.
Or
yeah.
Often the representation spaces are smooth, but in some cases the group action has stabilizers, in which case you get points where the representation spaces are not smooth.
I mean, when you're talking about an open surface, then the fundamental group is free, and so then the homomorphism space is
right.
nice.
Yeah, the difficulties arise when the conjugation action has stabilizers. So, for example, if you're quotienting at a point where the representation sends all generators of pi to, say, the maximal torus. Then conjugation action of T has fixed. So that can cause problems.
Right.
And you get which can result in singularities when quotient by conjugation action. The worst places are where the representation sends any elements to the sends any element of pi to the identity, then this also similarly causes singularity. So let's say all that causes singularities, because then this by is
Right.
by the entire G action under conjugation. So I think the problems are not that the representation space is singular, but that you get stabilizers in the conjugation action. And that may lead to the character variety being singular.
Right. And so going back to the to my first question, does the whole story then somehow lift to these homomorphism spaces, and then in some way?
I'm not aware that the representation spaces have that, you know, Hom pi G has a Poisson structure. I think only its quotient has a Poisson structure. Actually, I may be wrong. I may be wrong about that. We didn't study that, but it's possible that the representation that Hom pi G does have a Poisson structure.
Okay. Well, is there maybe another last question? That does not seem to be the case. Then let's thank Lisa again for her talk. And then I think we have a 5-minute break.
Okay, I'll see you in 5 minutes.
Yeah, thank you.
Thank you, Lisa. Thank you so much.
Thank you.